and welcome to this lecture. We looked at the definition of discrete random variables in the previous lecture. In this lecture, we are going to start describing the distributions of discrete random variables, and you will see we will slowly start de-emphasizing the sample space and experiment and outcome and all that, and we will emphasize random variables more and more. It's a very natural thing to happen in statistics. Okay, so the first thing you have to worry about when somebody gives you a random variable, the first thing you have to ask is what is the range of the random variable. Okay, the range is the set of values taken by it. Okay, usually in this class, at least we are thinking of it as subset of the real line, but I've always mentioned this caveat. There are texts which define random variables in a slightly more general way, and that's also useful sometimes, but most of the time it's taken to be a subset of the real line. So in this class, we will restrict it generally to subset of the real line. Okay, so usually when somebody defines a random variable, or somebody gives you a random variable, or gives you a problem that involves a random variable, always think of the range. Okay, so this is a lesson that I've seen students forget repeatedly. Okay, they'll start working, they wouldn't have thought of the range first. Okay, and then they'll get some very meaningless answer, and then they'll try to reconcile that with everything else. So always worry about the range of the random variable, because it can be a bit subtle. You will see as we go along, you will see some examples maybe where I'll bring out this aspect a little bit more clearly. Okay, so let's again do the simple examples we did with when you throw a die, and if you say x is the number shown on the die, then the range clearly is 1, 2, 3, 4, 5, 6, the same as the sample space. On the other hand, if I define a random variable to indicate to me whether the number shown on the die is odd or even. If it is odd, I say 0. If it's even, I say 1. Okay, then in that case, the range is just 0, 1. Okay, so once again, range of the random variable is very important. Once you start thinking of a random variable in an experiment, you first want to think of the range that you want to associate with that random variable. It gives you a lot of information about what you have to worry about when you start thinking of probabilities. Okay, so to just sort of tell you that it can be a bit non-trivial, okay, to just think of range of random variables in a complicated setting. It can be non-trivial, right? So I'm giving you the example of this IPL power play over now. I'll also mention a few others just offhand. Let's start looking at some of the random variables we defined in the previous lecture, right? Number of actual deliveries in the over, right? We know that the range here will start with 6, isn't it? In an over in cricket, you cannot have less than 6 deliveries, right? So it starts with 6, but it need not be always equal to 6. It can be 6, it can be 7, it can be 8, it can be 9. How large can it possibly be? I don't know. I actually went and looked at the ICC's rules of cricket. They're not very clear on this point. It looks like they don't actually specify any maximum number of deliveries allowed. What do I mean by maximum number of deliveries? Somebody can keep on bowling no balls, isn't it? So I think then the over will never end. I mean, I think in cricket one doesn't foresee such possibilities. They eventually see that eventually people will bowl legal deliveries and get out. So as far as I could check in the ICC rules of cricket, there is no actual limit on the maximum number of deliveries. But I think if people get frustrated, they'll just stop the over at some point, I think, or find another bowler or something like that. So eventually it will stop. But as far as theory is concerned, maybe we have to just have 6, 7, 8, 9, etc. Or you go look at the data and maybe you want to stop somewhere. Okay, but range starts at 6. That's important. The next random variable we looked at is number of runs in the over, and even here 0, 1, 2, 3, 4, 5, 6. Can you stop at 6? Really? Think about it. There are possibilities of getting more than 6 runs in one delivery. I mean, it could, don't think of the the free hit that you get. I'm not talking about that. I'm talking about just the one delivery. You can get overthrows, right? So for instance, you may run for 3 runs and somebody may overthrow a 4 for you. So that's 7 runs. Okay, or you may hit a wide no ball for runs. Even for that delivery, you get more runs. So it's not clear what is the maximum number of runs in a delivery is, and definitely in the over, it's really not clear what should be the maximum. So you may as well let it go 0, 1, 2, 3, 4, on and on and on. Maybe you should do that. Okay, but what about wickets? Number of wickets in the over. Okay, so here again you can start with 0, but what should the possible maximum be? Maybe, I don't know. 10 looks very, very unlikely. Maybe you want to assign a probability 0 to it, but still, it theoretically it's possible to go up to 10 wickets, right? So you can keep on bowling no balls and people can keep on getting run out, right? It's possible. So you can go from 0 to 10. Number of boundaries that way in the over 0, 1, 2, 3, it can keep going, right? So depends on how many no balls somebody bowls. Maybe there is some limit to it, but it can go like that. Okay. What about number of dot balls? Notice number of dot balls can be 0 and at most 6, isn't it? You cannot have more than 6 dot balls in any over, because if you had 6 dot balls, the over is complete, finished. Okay, so there's no point in getting 7 dot balls. It's not possible. Okay, so the point of this example was just to illustrate that in a real scenario, when you want to define a random variable, you really have to think about its range. I mean, it's not a very trivial problem. Okay, so you have to think about its range and then worry about what part is likely, what part is unlikely, all that you have to worry about when you want to think of random variables in practice. Okay, so one can think of other examples like, stock market. If you want to think of the stock market as the experiment and the stock prices as random variables, do you want to put a range to it? What kind of range do you want to use? What kind of probabilities you want to use? All these are important questions that people grapple with when they use practical applications of statistics. So this is all quite important stuff. Okay, so the range is not some dull thing. It's a very crucial aspect that you have to think about. Okay. Okay, so now we are ready to think of a discrete random variable. Okay, a random variable we will say is discrete if the range is a discrete set. So what is discrete? It turns out the strict definition of discrete is a bit of a complicated one. So we will use it in a very vague way. We will just say finite subsets are discrete. Okay, if you have a finite number of elements in the set, it's always discrete. The integers are discrete. All integer multiples of a number are discrete. Any subset of a discrete set is discrete. So generally, I will let you think about what a discrete set is. Think of just a finite set. Okay, so if something does not have an interval in it, it's discrete. Okay, that's probably a decent definition, and we'll leave it at that. We will not bother too much more about defining discrete. If there is an interval, okay, a comma b, an interval with a not equal to b, like 0 comma 1 or 1 comma 2. If there is an interval in your set, then it is not discrete. Okay, but if it's not there, then it's discrete usually. Okay, so that's a pretty decent understanding of discrete random variable. If you're interested, you can look up discreteness of sets. It's a bit of a complicated notion in mathematics. We won't define it very precisely, but I will assume you know what. So sort of you have an intuitive feel for what discrete is. It's just there's no continuous interval and all that in the set. Okay? It's just you jump from one place to the other all the time. Okay, so that's discrete for you. And in this lecture, in this week, we'll consider discrete random variables. We will also consider continuous random variables later on, where the random variable can possibly take continuous values in an interval and all that. Okay, so we'll look at that case a little bit later on. It's a bit more complicated. It's easier to start with discrete random variable. So we'll start with discrete random variables. Okay, so the most crucial thing. So like I said, the first one was the range of the random variable. Okay, so you have a random variable, you first find its range. Okay, so that's the first sort of skill you need to have. You need to nail down its range. Okay, the next thing you have to nail down, or next thing somebody has to tell you to fully specify a random variable, is the probability mass function. For discrete random variables, this is enough, and it's very easy to write down and describe. And once you give the PMF and the range, the PMF also includes the range in some sense, you have completely specified a random variable. Okay, so here is the definition. The probability mass function of a discrete random variable x with range set t is the function from t to 0 comma 1, to the interval 0 comma 1, and it's defined as the probability that x equals t for small t in the range. Okay, so that's the definition. It's maybe a bit of a long definition to unpack. Okay, so notice what a random variable is. A random variable is going to take you from the sample space to some range t. T is a subset of the real line, right? So we know that that's the range t. And the PMF, the probability mass function, is nothing but this. Okay, so it's basically probability that x takes a particular value in the range. Okay, so we'll give you a much simpler way of thinking of this. You can think of this like a table, like particularly for discrete random variables. But this is the proper definition. It's probability that x equals t. So now what is x equals t? Remember I talked about how to define events with random variable. x equals t is an event, right? So, probability that x equals t is probability of all outcomes in x that result in x taking value t. Okay. So, keep this definition in mind, this is very important. If somebody describes an experiment to you and then from there defines a random variable, okay, to compute the PMF of the random variable, you have to use this definition. Okay, the PMF, the probability mass function of the random variable taking a value small t is basically probability that the random variable itself takes the value small t, which is basically the probability of all outcomes of this experiment that result in the random variable taking value t. Okay. So, this is an important point to keep in mind. Okay. So, notice this other subtle little point. Okay. So, this point is also very important. Let us take a subset of the range set t. Okay. Instead of taking a single value in the range set t. Okay. So, instead of taking small t as a single value in capital T, I am going to take an entire subset of t. And then instead of just looking at the event x equals t, I can look at the slightly more complicated event where x belongs to this subset B. Okay. So, it turns out the PMF, using the PMF, you can find probability of x belonging to B. Okay. You do not need anything more. Okay. And the definition goes in a very simple way like this: probability that x belongs to capital B is probability of all outcomes that result in x taking values in B, and that is nothing but summation over all t. Now, notice this B here, it is not the whole t, it is this B here, the summation over all t belonging to B, the probability that x equals t, and that is simply the PMF added over all the values in B. Okay. So, the PMF I have defined for values in the range, this if you sum it up over all values in B, you get the probability that x belongs to B. Okay. So, what am I trying to convey here? So, the point is the probability mass function is the probability that the random variable takes one particular value, that is all. Okay, as simple as that. Okay, that is the definition here. So, you have one value that the random variable can take, probability that the random variable actually takes that value is my PMF. Okay, you go through all possible values here, you get the PMF. Now, once you know the PMF, it is enough to compute any event that you want defined using x. Okay, so that is the main point. Okay. So, any event, probability of any event using defined using x, sorry about that, defined using x can be computed using PMF. This is the main story. Okay. This is why the PMF is enough to completely specify a random variable. You do not need anything more if you have the PMF. Okay. You have a random variable, you have any event defined using that random variable, given the PMF, you can compute the probability of that. Okay. So, once you have the random variable and the PMF, you are done. Okay. In some sense, you are done. Everything any event you want to define using that, you can find. Is that okay? So, that is the usefulness of the PMF. Okay. So, let us do a few problems now. The problems I will do first will be of the following type. Okay. An experiment will be defined and a random variable will be defined. I will try to compute the PMF of that random variable. Okay. So, let me go ahead and do some of these calculations. So, in this experiment, a fair coin is flipped 3 times. Okay. So, that is the experiment. So, this is a problem where experiment is given and the random variable is defined in terms of what of the outcomes of the experiment, right. So, you have a fair coin is flipped 3 times. I am defining a random variable which is how many heads will appear. Okay. So, this is my random variable. Okay. Number of heads that appear is my random variable, and my second random variable, which will be the first flip, if any, that shows heads. Here is again another random variable that is defined. Okay. So, notice how these two are random variables. Okay. So, I will call this as x and I will call this as y. Okay. Now, I will make a table here, a short table. So, this is a method you can always use. Okay. So, suppose somebody gives you an experiment, you can make a table which lists all the outcomes of the experiment and the corresponding values taken by the random variable. Okay. So, this is a very useful thing to do. Okay. So, quite often I do this, and this is a very useful tool to solve problems. Okay. So, how do I write it down? I will write down outcome, the value of x, the value of y. Okay. So, write this. In fact, I can even write down probability of the outcome, right. So, maybe I will write down that. So, I say probability of outcome and outcome. So, these are simple experiments where all this can be really written down. So, what are the outcomes possible? You could have head, 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 tails, head, tails, head, head, tail, tail, sorry. And then you have tail, head, head, tail, head, tail, 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 head, and then tail, tail, tail. Okay, so those are the 1, 2, 3, 4, 5, 6, 7, 8 outcomes. I got that right. And the probability, it's a fair coin, so it's okay to assign 1 by 8 to each of them. Okay. And now what is x? X is the number of heads that will appear, 3, 2, 2, 1, 2, 1, 1, 0. Okay. And y is, which will be the first flip, if any, that shows head. Here it is 1, here it is 1, here it is 1, here it is 1, here it is 2, here it is 2, here it is 3, here there is none. Okay. Okay. All right. So, now this table completely describes my 2 random variables. So, wherever it is possible, if the experiment is very small, simply make this table. Okay. So, it will simplify your life a lot. You can easily do calculations. But sometimes it may be very laborious to do this table. Maybe you want to keep such a table in your head and do the calculations by hand quickly. You can do that also, but if you can make a table, right, so it does not hurt. So, from here you can easily find out the PMF. Okay. So, Fx, okay, first of all, before anything, I have to first find the range of x, right. The range of x is in 0, 1, 2, 3. Okay. And Fx of 0 is basically probability of TTT, that is 1 by 8. Okay. So, maybe I should write that down, probability of TTT, and that is just 1 by 8. Fx of 1 is probability of HTT, THT and TTH, and that is 3 by 8. Probability of 2 is probability of HHT, HTH and THH. Okay. That is again 3 by 8, and the probability of 3 is probability of HHH, and that is 1 by 8. Okay. So, that is the PMF of x. Okay. So, you can also find y and its PMF. So, y belongs to, okay, y could be none or 1 or 2 or 3. So, notice how this none is actually not a real line. So, maybe you want to keep it as, you could keep a value 0 here. Okay. So, for none you can say 0. If you say 0th toss, I mean it will never really happen, right. So, you could make this 0 here. Okay. So, Fy of 0 is just probability of TTT, that is 1 by 8. Fy of 1 is probability of the first 4 guys, right, 4 by 8, and Fy of 2 is 2 by 8, and Fy of 3 is 1 by 8. Okay. So, this is a way to fully specify these random variables. So, these kind of problems are very important. Okay. The experiment is given, a random variable is described in English in some sense, and you have to find its PMF, okay, find its range and PMF, and this is how you go about doing it. Okay, hopefully this was illustrative. This is a very simple illustration, very easy experiment to get your head around, and one can write down what is possible. Okay. Okay, so the next one is a little bit more complicated. You can't make a table here. You will see why you can't make a table. The numbers are too large, but nevertheless you can do the calculation without too much trouble. Okay. So, this is about a 3-digit lottery. Okay. So, there is a certain lottery where a 3-digit number is randomly selected from 000 to 999. Okay. This is a 3-digit number there are 1000 of them, 000 to 999. Okay. So, you should get tickets ahead of time, right, and your ticket will have a 3-digit number in it, right. If a ticket matches the number exactly, somebody generates the number randomly, maybe it's 123, right, I don't know, some number, and if your ticket is 123, then your ticket is worth 2 lakhs. Okay, you get 2 lakhs, you can go give it to somewhere and they'll give you 2 lakhs. If the ticket matches 2 of the 3 digits, it is worth rupees 20,000. Think about what that is. So, when you say 2 of the 3 digits, supposing you hold the ticket 123, okay, when will you get 20,000? Okay, you should get 1, 2 and something other than 3. It could be 120, 121, 122, 124, 125, 126, 127, 128, 129. Okay, or you could get so let me just give you an example. So, rupees 2 lakhs is exact match, that is not very difficult to see. Okay, and so when will you get rupees 20,000? So, here is an example. Suppose ticket is 123, you will get when will you get rupees 20,000? If the lottery number is 120, 121, 122, 124, so on till 129. Okay, there are 9 such numbers. It can also be 023, 223, sorry, so on till 923, isn't it? It can also be 103, 113, 133, so on till 193. Okay, so there are 27 possibilities. For that. Okay, so ticket is 123, you will get rupees 2 lakhs. If lottery number is 123, exact match, one possibility. Okay, otherwise it is worth nothing. Okay, it is 0 otherwise for any other lottery number. Okay. So, what is the distribution of x? Okay. So, you have a ticket, the ticket number is fixed. Okay. So, for every ticket number, whatever the ticket number may be, x has 3 possible values 0, 20,000, 2 lakhs. Okay. And what is that is the range. Okay. And what is fx of sorry, so put x, x belongs to 0, 20,000 and 2 lakhs. Okay. So, let us say this is t. What is fx of t? What is the probability of 2 lakh? It is 1 by 1000, isn't it? One possibility. What is the probability of 20,000? It is 27 by 1000. Okay. What is the probability of 0 now? Okay. You can go ahead and do a lot of calculation, but one easy way of doing it is say 1000 minus 28 divided by 1000, isn't it? These are the only 3 possibilities. If you get anything out of this 28, you are not going to get anything, right? They will change in any one of more than 2 places, it will vary. So, 1000 minus 28, whatever that is 1000. Okay. So, you can do that calculation, it is 972. Right. So, 972 by 1000. Okay. So, you saw this problem where making a big table with all the possible lottery outcomes is impossible. You will have 1000 lines, okay, and there is no point in doing that also, but you can define based on, you can take a simple example and work it out and you will quickly get the number of possibilities. Is this correct? Okay. So, it is correct for 1, 2, 3. So, if the ticket is 1, 2, 3, this is correct. What if the ticket is something else, right? So, let us say the ticket is, I do not know, you get say a ticket is 100. Okay. So, this can happen, right? So, maybe your ticket is 100, right? In this case, what will happen? if two of the digits in your ticket match, right, it is not 1, 2, 3, but let us say 1, 0, 0, then 2 lakhs is okay, 2 lakhs is still 1 by 1000. What about 20,000? You will need a different kind of lottery number, right. So, you will have 0, 0, 0, 2, 0, 0 all the way till 9, 0, 0, and then you will have 1, 1, 0 all the way till 9, no sorry 1, 9, 0 and 1, 0, 1 all the way to 1, 0, 9. Okay. So, in this case also you see 27 is okay, isn't it? So, rupees 2 lakhs is 1. So, it does not matter one possibility. So, it does not really matter what your ticket is, right. So, you may want to check that a little bit, right. So, try different possibilities for tickets and make sure logically also you sort of see that there are these, whatever the ticket may be, there are exactly 27 other 3-digit numbers in this way which will match in 2 places, okay, and they will all be distinct in some sense, right. So, you match one and then vary the third one, match 2, vary the second one. There is no way you can get, can you? I do not know, think about it. So, yeah, I do not think it will work for 2 out of 3, it is not going to work. So, this is this looks okay enough to me for any ticket, okay. So, not just for ticket 1, 2, 3, for any ticket you will have one possibility for 2 lakh, 27 possibilities for 20,000 and then 972 possibilities for the remaining other possibilities, which is 0, okay. So, this looks okay for any ticket, okay. So, this is true for any ticket. Okay. So, this needs a bit of calculation. So, you see that these kind of problems are very interesting, right. So, the experiment is defined to you, you understand the nature of the random choice in the experiment, and then a random variable is defined for you, and you have to now find the distribution of the random variable, and you have to use the the probabilities assigned to the outcomes of the experiment, very carefully form these events which are favorable to you for a random variable taking a particular number, then compute its probability. Is that okay? So, these kind of problems are very interesting. Sometimes they can be a bit difficult because it goes back to the computation of probability, but this is an important skill to have. I will tell you why this is an important skill to have, right. So, in an actual complex experiment, you may be interested in some random variable, but you may want to understand some outcomes in the experiment and how they work and what kind of probabilities you can put there and how that influences the random variable, okay. So, that understanding quite often will help you, okay. So, only when you solve problems like this that understanding builds up, okay. So, it is a good type of problem to solve.